Hi, so we're going to work through question 12 of the tutorial 7 for Inf1-CL. So, question 12. We're first going to need to define several concepts, which will help us work through the question. So first of all, we have rules. So a rule is of this form. Where all these symbols here, beta 1 through n, and alpha, are entailments. We call the things on the top assumptions, and we call the things on, or the single thing on the bottom, is our rule conclusion. We say rule conclusion because there's a different kind of conclusion for entailments, and it will get confusing later on. So what is an entailment? An entailment looks like this, where this symbol here represents a set of expressions in propositional logic, and A is a single expression in propositional logic. So this here is called premise, and this here we will call the entailment conclusion. So sometimes we won't just see one single symbol on the left, we'll see multiple symbols, like this. They can represent single expressions or sets of expressions, and sometimes it's not clear which. But the reason why we don't bother with symbols like this or bother clarifying whether it's a set or not is because it doesn't matter. The important thing is the whole thing is a set. So if that's a set and that's a single expression, we treat this as a set with all the things in this, all the things in this. We treat this as a set. If we write it like this, then we can call each of these expressions premises, or we could call a set of expressions a premise. The distinction turns out not to matter. So propositional logic, of course, we already know an expression propositional logic consists of, we're going to call this the set of atomic propositional symbols. So that's going to be X, Y, P, things like that. And an expression is going to be anything that combines our symbols together with these symbols, which we've seen before. Okay. So now that we have our definitions for rules and for entailment, we can build on these with more definitions. First, we're going to talk about what it means to be a valuation. So a valuation we can think of as a function from our set of propositional symbols, which we saw before, things like X, Y, P, etc. And that maps each of these to either true, which you write like this, or false. So we could think of a particular valuation as a table which maps each of these to either the value true or false. Now that we have a concept of valuation, we can talk about what it means for an entailment to be valid. So an entailment is valid if and only if any valuation that makes, show you our entailment here, any valuation that makes each of the premises true will also necessarily make the conclusion, the entailment conclusion, true. So we can write that as a logical implication. We can say if and only if V, our valuation, makes all premises true, and has to be all of them, then V must make the conclusion true. So the only way we can make this expression false, in other words, the only way we can make our entailment invalid is if we can find a V that makes all of the premises true and the conclusion false. If we find such a V, then we call it a counterexample. So a counterexample is a valuation that makes all of the premises true and the conclusion false. And from our definition here, we can see that if we find a counterexample, then this requirement for validity, this becomes false. And then we know that by finding our counterexample, we've made the entailment, or we've shown the entailment to be invalid. So if we can find a counterexample for an entailment, then the entailment is invalid. And if we can't, then it's valid. Or if we can prove this without resorting to counterexamples, that would also make it valid. But we're going to be using counterexamples to answer this question. So that's why it's important to have this definition of counterexamples. So with our definition of valid, and that's for an entailment to be valid, we can finally do what we need to do for the question, which is to define what it means for a rule to be sound. So our rule, it looks like this, is sound if and only if whenever all assumptions are valid then, and so this definition mirrors this definition, if all assumptions are valid, then our rule conclusion is valid. So again, the only way we can show that it's not sound is by finding, in fact, that's not important, I won't get into that. We want to prove that it is sound. So taking this, we can use what's called the contrapositive. So hopefully you've seen it before. If this is an implication, we call the contrapositive of it looks like this. If so these are equivalent, logically equivalent. So if this is true, if the top is true, then the bottom is true. We can see that by drawing a truth table. That's a good exercise. And it's called the contrapositive. And we're going to apply it to our definition of sound. So we can say, we can basically come up with a second definition for sound, an equivalent definition. And we're going to say, if the rule conclusion is invalid, then now we need to negate the fact that all assumptions are valid. In our contrapositive, this is A, this is B. We've negated B, row conclusion is valid, by saying row conclusion is invalid, not valid. Now, to negate A, we have to say at least one assumption is invalid. The opposite of all assumptions being valid is at least one of them invalid. Or they don't all have to be invalid. We only require making one assumption invalid for it not to be the case that all of them are valid. So we're going to take this even further now. So we're going to, the goal of the tutorial, of the question, as stated in the question, is to use counterexamples to prove soundness. So we can take this up and say a third equivalent definition for the rule to be sound is that if V is a counterexample to the rule conclusion, I'll just write alpha, then V is a counterexample to at least one of the assumptions. What we have here follows from what we have here, because for the rule conclusion to be invalid, as we've stated before, remember these are all entailments, so we're working with the definition of validity for entailments, which we just had on the board a second ago, and we had the definition that for it to be invalid, there has to be a valuation that is a counterexample. Okay, so we have a definition of sound. We have several definitions of sound, and the question actually asks us specifically to use this definition of sound for the particular rules that we have and show that the rules are sound. So we're going to do that. Okay, so I've written our definitions for sound and counterexample for reference here, and we're going to work through the proof that this rule here, called I, for identity, is sound. So first of all, we're going to identify the parts. So at the top here, we have no assumptions. This is going to turn out to be important. At the bottom, we have one rule conclusion, and that is this entailment here. Looking at this entailment, it has two premises, this symbol and X, and one entailment conclusion X. So in order to prove that this rule is sound, we're going to have to say that if we can find a counterexample to the conclusion, this entailment here, then it will be a counterexample to at least one of the assumptions. So first of all, our first step then is to find a counterexample for the conclusion. A valuation is a counterexample to a particular entailment if it makes all premises true. So we're going to have to say this is true. We're going to have to say this is true. And it makes the entailment conclusion false. So in order for V, I'm just going to write like this as a table. That's nicer. In order for V to be a counterexample to this rule, we're going to have to make this true and this false. Except, the problem is, to do that, we're going to have to make X both true and false. Now, V evaluation as a function from propositional symbols truth value, we can't have two values assigned to the same propositional symbol. It wouldn't be a function. So we have effectively shown here that we actually can't find a counterexample for the rule conclusion. So where does that leave us with the definition for sound? Well, remember, if we call this A and this B, we need it to be the case that A implies B for our rule to be sound. We remember from propositional logic that false implies true and false implies false. So it doesn't matter what's on the right hand side if we know that what's on the left hand side is false. And that's what we've just shown here. We've shown that it can never be the case that there is a counterexample to our conclusion. So this becomes true because left hand side A is false. So we've shown that our rule is sound, and we're done with this rule. Moving on to a slightly more complicated rule. So we have a more complicated rule here called the OR rule. Notice, important fact, there is a double line here between our assumptions and our rule conclusion. And we've not seen this before. So quick definition of this. This means that we actually have two rules here. So if we have assumptions and conclusion like this with the double line, what we're saying is we have two rules. We have this rule and we have this rule. And we're going to need to prove that both are sound in order to prove that this whole thing is sound. There's essentially two proofs. We need to prove this is sound and this is sound. So starting with it in the position we have here with this cell on top and this cell on the bottom, we're going to go through our procedure which we've just seen. So we want to prove that it's sound. So we need to find a counterexample for the rule conclusion, or in fact we need to find all possible counterexamples for the rule conclusion and show that for any one of them they will be a counterexample to at least one of the assumptions. So how do we find a counterexample to our rule conclusion? As before, we need to make all premises true and we need to make the conclusion false. So this is going to be true. In fact, I'll write like this. This is our function b, and that's going to make this true. We're going to have to make z false. I'm doing these because they're simple. More complicated, we need to make x or y true. So how does that fit in with our valuation? Well, there's different ways to do it, right? We know from our truth table that there are three ways to make x or y true. By the way, 1 is true and 0 is false. So we're going to have to use each of them, right? And each time we decide, say we make x true and y false, we have a valuation here which is a counterexample to the rule conclusion. And in order to, if we're starting off assuming that it's sound, in order to maintain our assumption that the rule is sound, we need to show that this valuation is also a counterexample to at least one of these. So we do it for the first one. So we need to find an assumption, and it doesn't matter which one. We only need to find one. We need to find an assumption where this is a counterexample to that assumption. So if we look at the first assumption, we need to make this true, and this false. X true and z false. So in this case, our valuation x is true, z is false, this symbol is true. So we're done. We've already found. We call this assumption 1 and assumption 2. Then this assignment of x and y values will make assumption 1 false. We're going to keep track of that. Moving on to the next possible counterexample for the rule conclusion, because we need to show that any of them will lead to a counterexample to one of the assumptions. So moving on to the next one, we have x is false and y is true. So again, we're looking for any assumption. So we look at the first one. This is true. We need to make this true, but no, this is false. So this valuation is not a counterexample to assumption 1. We move on to assumption 2. This is true, y is true, z is false. So things on the left are true, thing on the right is false, so we're done. We found a counterexample. We found an assumption where this valuation is a counterexample to that. Finally, there's only one more possible valuation which will make the rule conclusion, which is a counterexample to the rule conclusion. That's this. As we've seen before, the fact that x is true, this is true, and sorry, I'll write it first. They're both true now. The fact that x is true, this is true, and z is false means this is a counterexample to 1. As it turns out, it's also a counterexample to 2, but we only need to find 1. So that's us actually done with this rotation of the rule. If we pretend this is a single line, we're done, but it's a double line, so we're going to have to do the same thing again, but with our assumptions and conclusions reversed. Just to summarize, what we did was we found every possible valuation that is a counterexample to the rule condition, the rule conclusion, and for each such valuation, we've shown that is also a counterexample to at least one of the assumptions. And that is enough to show that our rule is sound. So moving on to the reverse. Okay, so same again, except we have our assumptions and conclusions reversed, and this should be a single line. So remember, we pretended last time that the double line was a single line. Now it's actually a single line. So this is a separate rule from before, and we need to prove that it's sound from scratch. So same again, we need to find counterexamples, all possible counterexamples to our conclusion. In this case, there's 2 entailments which form the conclusion. So we need to find a valuation that is a counterexample to both entailments. So our valuation is going to have to make this symbol true, because it's there. It's going to have to make x true. It's going to have to make y true, because these are all the symbols which are on the left-hand sides of our entailments. And it's going to have to make z false, because z is a symbol that is luckily on the right-hand side of both entailments. So this is, in fact, the only valuation which is a counterexample to the rule conclusion. So this actually makes our job easier than before. All we need to do is show that this valuation is a counterexample to at least one of the assumptions. There's only one assumption, so we only need to show that this valuation is a counterexample to the assumption. So same again, we need to make everything on the left true and everything on the right false. This is true. X or y is true. We know this because x is true and y is true. And z is false. So actually, we're done. So that will conclude question 12. The only other note that I will make is the rule cut has a single line, not a double line, so you only need to prove it one way. The rest of the and implication are double rules, so as we did here, we're going to have to prove it both ways. Prove it once in the way given and then once flipped. That's the meaning of the double line, remember. Okay, thanks for watching.